Hello everybody. So we are finally ready to start talking about quantum algorithms. And so the rest of this course will be devoted to quantum circuits, quantum algorithms, analyzing them. Okay, so before we get there, let's talk about something that's very basic and which forms the basis of quantum algorithms. This is why quantum computers have this potential to be exponentially powerful. And this is one of the great paradoxes of quantum mechanics. It's to my mind the most counterintuitive aspect of quantum mechanics, and it's one that was missed for the good part of a century. So it has to do with this exponential growth. So let's go back and remember what a qubit is. So remember our picture of it is the electron in a hydrogen atom. Can either be in a ground state or in an excited state, which we think of as 0 and 1. And of course, quantumly, the superposition principle tells us that the electron can be in a superposition of these two states, which we can write as a unit vector in a two-dimensional vector space. Now, if we add one more qubit, so we have a two-qubit system. Classically, this could be in one of four states, 2 bits. The quantum state is a superposition over all these four states, so it's a unit vector in a four-dimensional complex vector space. Now we can keep going. If we add one more qubit, so now classically, we'd be in, since there are 3 bits, they can represent 8 possibilities. But once again, the quantum state of this system, of this 3-qubit system, is a superposition over all these 8 possibilities, which means that it's a unit vector in an 8-dimensional complex vector space. Why 8? Well, another way of seeing it formally is, we are gluing together 3 different Hilbert spaces, each of 2 dimensions. And the way we glue them together is by taking tensor products. And so when we take a tensor product of C2 with itself 3 times, the dimension multiplies and we get an 8-dimensional complex vector space. Now we can keep going this way, and what if we have an n-qubit system? So now n bits can represent 2 to the n different possibilities. And again, the quantum state is a superposition over all these 2 to the n possibilities. So it sits in a 2 to the n dimensional complex vector space. Again, it's C2, tensor, C2, tensor, C2, n times for a dimension of 2 to the n. Now, this kind of exponential growth in dimension is quite startling. So even for n equal to 500, 2 to the 500 is an unimaginably large number. It's larger than the number of particles in the universe. It's larger than the age of the universe in femtoseconds. And so if we were thinking about this as computing power of the system, well then this is more computing power than you could get by a computer which was working for the age of the universe and had this really incredibly quick cycle time. And moreover, it was not just one computer, but it was a parallel computer where every particle in the universe was one of its cores. So this is truly extravagant. If we could ever exploit this full computing power, this would be truly extravagant. Okay, so now just a very quick reminder about where this exponential growth comes from. So this comes from tensor products. Remember, if you have a k-state system represented by k-dimensional Hilbert space, then you can describe the state of this system with k parameters. And similarly, if you have another system which is an m-state system, so you have m parameters required to describe it. And now, what happens if you put these two systems together? So if these were classical systems, you could describe the composite system using k plus m parameters. But when you take tensor products, when you take a tensor product of these two systems, which is what you have to do quantumly, then the number of parameters you need to describe this composite system is k times m. Right? So, another way of saying this is, if this space is c to the k, this one is c to the m, those are the two Hilbert spaces, then this composite system is represented by ck tensor cm, which is isomorphic to c to the km. So the dimensions multiply, and this is where we get this exponential growth from, if you take many, many copies of this. And the reason you have this increase in dimension is because of entanglement. So to describe the state of this composite system, it's not sufficient to just describe the state of A and the state of B, because these two systems will in general be entangled. And so you have to describe the state of the system by describing a superposition over k times m possibilities. Okay, so let's go back and look at all this a little more pictorially, right? Just to make sure we understand all this. So we have an n qubit system. Now, what the superposition principle tells us is that the state of the system is a superposition over all the classical possibilities. It's a unit vector in this exponentially large, exponential dimensional Hilbert space. Okay, so the state of the system in particular is a superposition over all n-bit strings x, where each has its amplitude alpha sub x. And everything is normalized, so the sum of the squares of the magnitudes of alpha x is 1. Now, also the state of the system, how does it evolve? Well, the way it evolves is by the application of, for our purposes, the application of quantum gates. So we might pick two of these qubits and apply a quantum gate to it, which is represented by a 4x4 matrix tensor with the identity on all the rest of the qubits, because we are leaving them alone. And the result of this is that we take this Hilbert space, this complex vector space, and we rotate it. And as we rotate it, the state of the system changes, and all these complex amplitudes get updated. Okay, so this is an important point, that even though we are actually working on just these two qubits alone, so the effort we are putting in is we are doing something, we are applying some Hamiltonian to these two qubits alone. So the effort required is proportional to 2. But behind the scenes, what's happening is that this entire Hilbert space got rotated, and all of these amplitudes, the 2 to the n amplitudes, which represent the state of this n-qubit system, get updated. Okay, so maybe let's take a closer look at what this might look like. So, for example, let's say that we had a n-qubit system, and we happen to apply a gate. Let's say we apply to this qubit, we apply a Hadamard gate, right? So what happens? Well, I claim what happens is that if you look at, pair up the alpha x's, so you look at x of the form 0 x prime and you look at x of the form 1 x prime, right? And you ask, what happens when you perform a Hadamard? Well, you see, you're only performing a Hadamard on the first qubit. The rest of the qubits are left alone, so x prime just stays x prime. But what happens to the first qubit? Well, when you apply the Hadamard, what happens is that the new amplitude of 0x prime is going to be equal to alpha 0x prime plus alpha 1x prime over square root 2. Right? Because under the Hadamard, what happens is that 0 goes to 0 with amplitude 1 over square root 2, and 1 goes to 1 to 0 with amplitude 1 over square root 2. And so these amplitudes add up in this way. On the other hand, 1x prime ends up with amplitude alpha 0x prime minus alpha 1x prime over square root 2. Okay? But this is true about all the possible n-bit strings x. So what we've done is we've paired up all the n-bit strings, and then what this gate does is it takes the amplitudes of these two strings and then it mixes them up in this way. So what it's doing in effect is it's updating all the 2 to the n amplitudes alpha sub x in this way. Okay, so now let's think about what this is telling us. So what this is saying is, first of all, for this 500 qubit system, 500 hydrogen atoms, so microscopic, really tiny system, nature must keep around somewhere 2 to the 500 pieces of scratch paper, each with a complex number written on it. Well, not it must, but it's as though it is, right? It's as though nature has stored all these 2 to the 500 amplitudes somewhere in its own internal memory. Okay, and then every time we perform a simple operation on these qubits, even a local operation like a Hadamard transform, something very simple, nature is busily scratching out these complex numbers, the 2 to the 500 of them, each from its scratch paper, and writing new ones in their place. But 2 to the 500, as we saw, is larger than the number of particles in the universe, larger than the age of the universe in femtoseconds. So now you could marvel at all this, and you could say, how is nature able to carry out this sort of extravagance? You might even say, I just don't believe it. I don't believe quantum mechanics is correct. Because how could it be that, that a theory which claims that nature behaves in such a ridiculous fashion could possibly be true? The other way you can think about it is you can say, okay, let's assume that nature does this. What are we going to do about it? Can we use it in some way? And then you can say to yourself, well, what's a computer? A computer is just a physics experiment, right? If you look, it's a nicely packaged physics experiment, but if you look underneath the hood, you have wires and transistors and currents and voltages and so on. And so a computer is just a way of tricking nature into solving a problem of interest to you. So if nature is working so hard at the quantum level, why should we be doing our computation at a classical level? Shouldn't we be implementing computers at the quantum level? And that's the thought behind quantum computation. Okay, so there's a bit of a rub. The problem is that this is the private world of nature, this exponential superposition. As soon as you look at the system, you only see one of the n-bit strings with probability alpha x magnitude squared. This is meant to be an alpha. Okay, so it's as though nature is this. It's in quantum mechanics, nature behaves like one of these people where they have this. They have this very rich life, but it's all private. And you ask them, hey, what's up? And they say, oh, nothing ever happens. Right? So the question behind quantum computing really is, we have a theory that nature is exponentially extravagant. But on the other hand, we have a measurement postulate which seems to suggest that nature covers her tracks. And maybe there's a way that nature never allows us to look behind the veil and see what's going on. And so the field of quantum algorithms, quantum computing, is trying to peel this veil aside and trying to, there's this tension between the measurement axiom and the first two axioms, the superposition and unitary evolution. And the field of quantum algorithms and quantum computing tries to exploit this exponential power despite the limited access that the measurement axiom affords us.